Imagine you've spent your entire life building a puzzle, thousands of pieces, years of careful work, and finally, the picture is almost complete. You step back, proud, satisfied, and then someone hands you a single new piece that doesn't fit anywhere. Not on the edges, not in the middle, not anywhere at all. You stare at it, and slowly, with a creeping sense of unease, you realize the puzzle you've been building might not be the picture you thought it was. That is exactly where humanity stands right now. A single telescope, a machine made of mirrors, math, and human ambition, has pointed itself at the oldest light in the universe, and what it has seen has left the world's greatest cosmologists stunned, arguing, and quietly rewriting everything they thought they knew. The James Webb Space Telescope hasn't just given us prettier pictures of space. It has cracked open the foundation of our cosmic story and revealed something underneath that nobody was fully prepared to find. And what it found isn't just surprising. In the most profound, bone deep sense of the word, it is terrifying. Now, before we dive into the deep end, let's set the stage. Because to understand why Webb's discoveries are so earth shaking, you first have to appreciate how solid, how confidently established, how beautifully complete our old picture of the universe seemed to be. For decades, scientists weren't just guessing about the cosmos. They had built a model, refined over generations, tested against mountains of data, a framework so successful it had become almost unassailable. It was called the Standard Model of Cosmology, and its technical name is Lambda CDM. This model wasn't a rough sketch, it was a masterpiece of human reasoning. It explained how the universe began in a hot, impossibly dense singularity around 13.8 billion years ago. It explained how, as space expanded and cooled, gravity began pulling matter together across vast scales. It described how invisible clouds of dark matter formed the scaffolding of the cosmos, and how ordinary matter, the gas and dust made of atoms, fell into those dark scaffolds and began to condense, heat up, and ultimately ignite into the first stars. It traced the long, patient, billions of years journey from those first faint stellar sparks to the colossal spiral galaxies, galaxy clusters, and cosmic superclusters we see surrounding us today. And it fit. The cosmic microwave background, the faint thermal afterglow of the Big Bang itself, matched the model's predictions almost perfectly. The distribution of galaxies across the observable universe matched. The abundance of hydrogen and helium in the cosmos matched. Lambda CDM wasn't just a theory, it was a triumph of scientific civilization, but there was one era it had never truly been tested against: the very beginning. The first few hundred million nickname that sounds like it belongs in a science fiction film, the red monsters. These are galaxies, some of them observed as they existed in the first billion years after the Big Bang. Objects that, under the old model, should not yet have had enough time to accumulate significant mass. And yet here they are, behemoths containing hundreds of billions of stars, nearly rivaling the Milky Way, our own galaxy, which took nearly 13 billion years to build in total stellar mass. One astronomer described the experience of seeing them in Webb's data as finding a toddler that weighs 100 kilograms. The numbers simply don't add up within the timeline our models describe. Webb then pushed even further back in time and confirmed the existence of a galaxy with the designation JADES GSZ140, shining in the light it emitted a mere 280 million years after the Big Bang, a moment when the universe was barely 2% of its current age. And this wasn't just a faint, simple smear of light. Analysis of its spectrum revealed the unmistakable chemical signatures of carbon and other heavy elements, elements that can only be produced inside stars and released into space when those stars explode and die. Their presence in a galaxy this ancient, this early, means something staggering. An entire previous generation of stars had already been born, lived out their lives, and died, all before this galaxy even fully formed. In the first 280 million years of cosmic time, the universe had apparently already completed an entire stellar life cycle that our models had never imagined happening so quickly. The implications of that single finding alone are enough to keep a cosmologist awake at night. And yet, even that is not the strangest thing Webb has found. Scattered across its deepest survey images is a class of objects that no one has been able to definitively explain yet. Tiny, intensely bright, reddish points of light embedded in the early universe, given the working nickname, the little red dots. These objects are puzzling on every level. They are compact, far too compact, and yet far too luminous for their size, according to everything we understand about how matter behaves. Some astronomers believe they are supermassive black holes caught in a ferociously active phase of growth in the earliest cosmic era, gorging on surrounding gas and blazing with radiation. Others have proposed something even more radical, that these objects represent a class of stellar body we have never encountered before, hypothetical behemoths called supermassive stars. Single stellar objects potentially containing 1,000,000 times the mass of our Sun. Structures so extreme they would exist at the absolute physical limit of what matter can do. Whatever the little red dots turn out to be, they share one quality that runs through all of Webb's most shocking discoveries: they should not be there. Not yet. Not according to the universe as we understood it, and they are not alone in that impossible club. Webb discovered a gravitationally bound cluster of 5 galaxies already locked in a complex, chaotic dance of merging and interacting with one another. All of this happening when the universe was only a few 100 million years old. Merging galaxy groups were supposed to be a phenomenon of a much older, more evolved cosmic era. And perhaps most hauntingly, Webb detected a galaxy designated JADES GSZ131, blazing with radiation from just 330 million years after the Big Bang. And here is the truly eerie part: that radiation should have been stopped cold. The early universe at that point in time was filled with a dense fog of neutral hydrogen gas, a primordial shroud that should have absorbed virtually all energetic radiation trying to pass through it. But Webb saw the galaxy shining through that fog anyway, which means something had already blasted a vast transparent bubble through the surrounding hydrogen, something enormously powerful, operating at a scale that, again, our models had not predicted for that stage of cosmic history. The universe, apparently, was far busier far more explosive, and far more creative in its infancy than any theory had dared to suggest. Now, here is where many people expect the story to pivot into reassurance, where the scientist steps to the podium, adjusts their glasses, and explains calmly that yes, these are anomalies, but we found a small tweak to the equations and everything is fine now. But that's not what's happening. What's happening instead is something rarer, something that only occurs at the true turning points of scientific history. The discoveries are piling up faster than the explanations, and one specific puzzle that Webb was partially hoped to resolve has instead been confirmed as deeply, stubbornly real, a problem that now points almost certainly toward physics that humanity has not yet discovered. It is called the Hubble tension, and it is one of the most unsettling open questions in all of modern science. The tension emerges from two completely independent ways of measuring how fast the universe is expanding. The first method uses observations of the nearby universe, distances to galaxies measured using a well-calibrated chain of techniques anchored by pulsating stars called Cepheid variables and brilliant stellar explosions called Type 1a supernovae. This gives a certain number for the expansion rate, a number called the Hubble constant. The second method takes a completely different approach. Instead of measuring the universe's expansion directly, it takes the known physics of the early universe, the properties of the cosmic microwave background, the afterglow of the Big Bang, and calculates what the expansion rate should be today based on those initial conditions. And this method gives a different number, not wildly different, but consistently, persistently, maddeningly different. The two measurements disagree at a level that statisticians call highly significant. For years, many scientists assumed the discrepancy would dissolve once better instruments removed the measurement errors. Webb was supposed to be that instrument. Its infrared precision was expected to nail down the distance measurements so accurately that one side of the tension would simply collapse. Instead, Webb confirmed the local measurements with extraordinary precision. The tension didn't collapse, it hardened. It became more real, not less. And what that means is both simple and staggering. The discrepancy between those two numbers is not an error in our telescopes. It is a feature of reality, something in the physical makeup of the universe itself, some ingredient, some force, some property of space and time that we have not yet identified, is causing the cosmos to expand differently than our best models predict. The universe is hiding something from us, something fundamental. So, what does all of this add up to? Is the Big Bang Theory wrong? Are we back to square one, starting over from scratch? The answer, and this matters enormously, is no, not exactly. The evidence for a hot, dense beginning to the universe remains overwhelming and is not seriously challenged by Webb's discoveries. The cosmic microwave background still exists. The primordial abundances of hydrogen, helium, and lithium still match Big Bang nucleosynthesis. The broad architecture of the Lambda CDM model still stands. But the detail work, the mechanics of how structure formed, how fast galaxies grew, how quickly the first generations of stars burned through their lives, how the universe's expansion has evolved, all of that is now in serious, genuine scientific dispute. Think of it this way. Imagine you have a blueprint for a car, a well-designed, sensible blueprint that correctly describes the overall shape, the number of wheels, the basic systems. And then you build the car according to that blueprint, and you discover it accelerates 6 times faster than the blueprint specifies. The blueprint isn't entirely wrong. But the engine? The engine is nothing like what was drawn. That is the situation cosmology finds itself in today. The blueprint is largely correct. But the engine of the cosmos, the mechanism by which it builds structure, grows galaxies, forges stars, and expands through space, is operating according to rules we do not fully understand yet. We live inside a sphere of observable space stretching roughly 46.5 billion light years in every direction. That sphere has a hard boundary, not because the universe ends there, but because beyond it, space itself is expanding so fast that the light from those regions will never reach us, not in the entire remaining lifetime of the cosmos. We are, in a very real sense, cosmically isolated, islands of observability in an ocean of unreachable reality. For most of human history, we didn't even know that ocean existed. For most of modern science, we thought we had at least mapped the shoreline. Now the James Webb Space Telescope has sailed out toward the horizon of our observable universe and returned with reports of a coast.